Welcome to Go With The Flow. As David mentioned, we are both engineers, and although we're different kinds of engineers, I'm a chemical engineer, Brian is an aerospace engineer, one of the things that we have in common is that we work with fluids. And that's what today's show is going to be about. It's going to be all different kinds of fluids, properties of fluids, fun things you can do with fluids, smelly things you can do with fluids. Yeah, you guys are going to have a great time up front. So before I start, I always have somebody that helps me out by drawing the numbers for you all. And so I'm going to call him up. Come on up. This is my helper today. His name is Luke Roberts. He is you can tell. Okay, how old are you, Luke?
10.
And what school do you go to?
Bear Creek.
He goes to Bear Creek. So he's going to be the one that's going to draw the numbers to choose everybody that wants to come up front, okay? And actually, he'll also be able to watch things from up here. So the first thing we always start with is talking about what is a fluid, okay? Oh, you want to tell me. Tell me. Okay.
Liquids.
Go ahead and talk into the microphone.
Liquids. Their atoms are moving kind of fast, but not all that fast. Some have viscosity.
Okay, don't ruin our show.
That's right.
We'll be talking all about that. And as he said, fluids are things that molecules, they sort of move and they're sort of far apart. But one thing he said, and this is one of the things that we want to talk about, is if you think of fluids, you think of liquids, right? Water, milk, oil, things like that. What else are fluids? Gases. And last time when we did our fluid show, we focused mostly on liquids. This time, we're going to give gases a chance as well, and we're going to talk about the properties of both of them. So we thought we'd throw in a little science, okay? So we want you to remember one thing from this. When we talk about fluids, we talk about something called the Reynolds number. And if you're a famous scientist, sometimes you can have a number named after you. And I'm sure it was Dr. Reynolds put together this number called the Reynolds number, and it's abbreviated RE, and it tells you what kinds of flows that you might have. And as scientists and engineers, Brian and I have always wanted a number named after us. And I teach heat transfer in the university, and I opened up the book and there was the JA number. And I thought, the Janet number. It's named after me. But actually it was the Jacob number, and it was named after Dr. Jacob. So we're going to talk about the Reynolds number and what it shows about flow. And as a chemical engineer, I'm interested in flows generally of high Reynolds numbers, low Reynolds numbers. As an aerospace engineer, Brian is interested in much higher Reynolds numbers. And what Reynolds numbers deal with are properties: density, viscosity, as well as velocities. So what we're going to start with is to talk about some of the properties, and in particular, we'll start with density. And for this, we need a helper. Okay, Luke. What number is it?
110.
Does anybody have 110? Oh, look at that.
Oh, right here in the front.
Okay, come on up.
Like somebody knows you.
Yep.
You want to tell us your name?
You know him.
Okay, my name's Sam.
And what
Bear
school?
Creek.
Bear Creek.
Oh,
Okay.
this was not a fix, I promise. Okay, so what we're going to do with Sam is he is going to show fluids of different densities. And what density really is, we define it as, you want to tell us? Okay.
Density is how dense an object is. Higher, like solids, I think have very low density.
High density, right.
Gases have low density. And why like a rock sinks is because it has a higher density than water.
Exactly. So what he was saying is density is really, the way you would view it, is how much it's mass per volume, or really the way you would look at it is sort of how much it weighs. And so what we do is we take fluids of different densities, and if we line them up in something like this, we would expect the fluids that have the highest densities, where? To be on the top or the bottom? The bottom. And the ones with the lowest densities would be on the top. Okay, so let's start with
Which end you want to
the
start with?
red one.
Okay.
Okay, this is corn syrup. What do you think? Do you think corn syrup has a high or a low density? It's a high density, so go ahead and pour this in. I was going to say, pretty disgusting, huh? No, you like that, huh? It's cool. Okay, let's try this. This is glycerin. Is glycerin a high density liquid, would you say, or a low density? It's high. The question is it higher or lower than corn syrup? And how would we tell? We'll pour it in, and if it's higher, what will happen? It'll go to the bottom. Let's see what happens here.
Thank you.
Unfortunately, the colors are kind of blending, but if you can see,
It'll
you
start
can
to
see there
separate.
still is a break here where the corn syrup is on the bottom and the glycerin is the next layer. This is water. Do you think water has a higher or lower density? It's lower. So pour it in carefully up there, and hopefully it won't blend too much.
That was a good one.
Okay. Now here's another interesting question. This is oil, okay? Do you think it has a higher or lower density than water? How many people think higher? How many think lower? Okay, let's see who's right. Go ahead and pour this in. Okay, is it on the top or the bottom? So is it higher or lower? Exactly, it's
Okay,
lower.
thank you.
So this is how you can make your own density rainbow with fluids of different densities. So that's the first property of fluids that we talk about. The next one is viscosity, and which is what you had mentioned. And viscosity is actually sort of the stickiness, right? And most people think that viscosity and density are related. And they're both molecular type properties, but just because something is denser than something else doesn't mean that it's more viscous. And what we're going to do is we're going to take three fluids here, three of the ones that we used before. We have glycerin, we have water, and we have oil. All right? And this was the densest, followed by this, followed by this. And what we're going to do is put a ball and drop it. And the faster it drops, the less viscous it is. Or the slower it drops, the more viscosity it has. So we need somebody to help out? What number?
100.
Oh. Anybody have number 100? No? All right, let's try another number.
Oh, he has it right here.
Oh, come on up. All right, and your name is?
You gonna step over here?
Yep, you have to.
And your name?
Brayden,
What school do you attend?
Pine Lane Intermediate.
Okay. So you're going to show us here, with
Come over here.
these three, which one of these fluids is the most viscous and which one isn't. So first we'll start with glycerin. And put it in glycerin. Wow. Glycerin is very viscous. And in fact, if you come back here next year, this may have dropped to the bottom, but I doubt it. Okay? So we know that that's very viscous. Now, if you recall, the water is denser than the oil, right? So which one do you think is more viscous? We'll put these in at the same time, and the one that travels slower, okay, we'll try
They're
some
floating.
other. Okay. Well, I guess these balls are a little, not
They're
quite-
less dense than
they're
either.
less dense. So actually, if we sit here for the next hour, aha. No, I don't think we're going to have to get heavier
any metal
balls
balls?
than this. Do you know?
Metal, I don't know, these are, I mean,
How
They're
about
all-
this?
yeah,
How
they're
about
all
if I tell
float.
you what would have happened
Yep.
if it worked? We always have a discussion on which experiment do we
That would
think
probably work.
won't
Anything
work.
other than wood.
This was not on our list, because this one has worked a number of times.
We'll come back to this one.
We'll come back to this with heavier balls, but what happens is the oil is, even though it's less dense, is more viscous. So when you put balls in them, this one falls a lot more quickly in the water than it does in the oil. Well, thank you. I'm sorry that didn't quite work for you.
Okay.
Aha.
Are these aluminum?
they're aluminum.
All right. We'll see. We have that maybe these. I don't know if they're going to be heavy enough either.
There you go.
Okay. Do you have two more? Okay. Come on up, since you didn't get your opportunity before.
Excellent.
We're going to
There we go.
try. These are both
These are little
bits of
aluminum pellets.
Okay. And you drop them at the same time, and the one that takes the longest to get to the bottom is the more viscous. So put them both in. Oops.
Oh, you missed.
You can try one more. Ready?
There we go.
Okay. Did everybody see that? It does take longer for the oil. Thank you. The next thing that we're going to talk about when we talk about viscosity is involved with something called Newtonian versus non-Newtonian fluids. And most of the fluids that we see are Newtonian fluids. And what that means in mathematical terms is that the viscosity is basically a constant when you stress it. What are the most fun fluids, however, are those that are non-Newtonian. And I'll give you an example of one, and that's toothpaste. Why, when you open up the toothpaste, does the toothpaste not just come out? Because, why? It's sticky, and that's what viscosity has to do with. Because it doesn't have enough force, exactly.
You said
And
Because it doesn't have enough force.
to push it out. And that's called a Bingham plastic. A Bingham plastic is a non-Newtonian fluid that doesn't flow until you push it enough. And then once you push it, it acts like a fluid, and it flows. Other non-Newtonian fluids are things like ketchup. Ketchup, the more you stir it, the thinner it gets, the less viscous. And that's why if the ketchup doesn't come out, you bang on the jar, you take a knife and you stir it. What you're trying to do is make it thinner. We also have fluids that are called shear thickening. And this is one that we're going to do right here. We need another volunteer. Right here.
81.
81.
There we go, in the very back.
Okay.
Comes-
Come on down. Okay.
Come over here to the front. Your name?
My name's Sienna.
What school do you attend?
I go to Whittier Elementary.
Okay, Sienna.
Okay, Sienna, you're going to make a non-Newtonian fluid. This right here is cornstarch. This is a spoon. That's yours. And now we're going to pour some water in it and start stirring. So what's happening as you're stirring this? It's, say it again.
It's getting harder to stir.
It's getting harder to stir. The reason it's getting harder to stir is that cornstarch is a non-Newtonian fluid. It's called a shear thickening. The more you stir it, the more viscous it gets, so the harder it is to stir. So anytime you put cornstarch and water together, that's what you get. And what you'll find is if you just pour it, it's a liquid. If you bang on it, it becomes a solid. And that's because it's a non-Newtonian fluid. So let's show them this mess that we made. See, it looks like a, ooh, this is a perfect one that you made. But if you go like this, it's like a solid. But if you stir it, it's like a liquid. And apparently, I've never been there, but apparently that's what quicksand is like. So if you ever get caught in quicksand, be gentle, okay? Let it flow if you want to get out instead of fighting against it, okay? Thank you, Sienna. This is the best batch of cornstarch we've ever made. Okay. Now the next one is something that you all are going to do. But I need another volunteer, pick a number, to help me make this while you guys are making yours in your seats.
101.
101? Come on down.
Up here. Turn around this way. Your name?
Caitlin.
And what school do you attend, Caitlin?
Monarch K8.
Okay. Caitlin is going to help me make a polymeric fluid or a polymer. You should have two little containers. One has something that's white in it. So open up that container, and it should look like this. Okay. You want to hold that?
Open carefully.
Yep. Now, ew, right? You want to see real ew. Open up your other container and take a little bit of the liquid and pour it into your white stuff and then stir. Yeah, you might have some. What are we getting there?
How much liquid should they pour? About half?
First start by pouring about half, and then so what are you getting? Exactly. You should get something like that.
You know, turn around and show it right there.
That's pretty cool, isn't that? Yeah. It looks kind of like cooked egg whites. And actually, what it is you are doing your own reaction. You're taking a polymeric type fluid, which is your white fluid, and you're adding something that cross-links it. So you're actually making a cross-linked polymer, which has totally different properties than your fluid before. Do you want that? Thank you very much for helping. Oh, another fine mess. We're going to move on to even yuckier stuff. Yeah, okay? And to start, I'm going to talk to you about a property called pH. And pH tells you whether something is acid or base. And the reason you might want to know this is if you are doing a reaction, which is something that a chemist or a chemical engineer might do, and you need to have a certain pH, then you need to test for it. So I need a volunteer now to come up and help me test some pH.
82.
82.
Last call? Okay.
All right, another one.
1.
Oh, number 1.
Your name is
Heather.
Heather, and what school you attend, Heather?
Bear Creek.
Bear Creek.
Gosh, did all of Bear Creek come out? So we have something called a universal indicator. And a universal indicator tells us whether we have something that's acidic or basic. So here it is, and normally it's a green color. So we'll see how it changes color depending on what we put in it. So put a couple of drops there. And then you have to squeeze a couple. And maybe a couple more. Squeeze hard. Okay. This sort of stayed the same color, a little bluer. Let's try this one. You have to really squeeze it hard. Okay, this one turned bluer. And the reason for that, this was sodium chloride. Sodium chloride is neither basic nor acidic, so it stays the same color. However, sodium acetate is slightly basic, so it turns blue. Acetic acid, we know this is vinegar. Okay? What is it, an acid or a base? Acid. So let's see what color that turns. Squeeze a few. Look at that. It turns red. Finally, sodium hydroxide. Is that an acid or a base? That's a base. And in fact, sodium hydroxide is what you use to clean out your drains. So let's see what color that turns. Oh. So that turns purple. And that shows us that we have a base. So thank you for helping out. You know, one of the things that I am most famous for is this
Stand up here.
particular experiment. So,
Yeah, you stand over here with Janet.
okay.
All right.
And your name is? And where do you go to school? Okay, here you go. I'm actually today going to give out my famous recipe for elephant snot. Okay. Oh, he likes it. He says it's cool. So the first thing you do, if you have just whites, all natural egg whites, for preparing healthy foods. I don't think they had elephant snot in mind. So 2 spoonfuls of that. And if you don't have egg white, dried egg white into here, instead you can use just regular 2 egg whites. Then
There you go.
a little detergent. This is Tide. You can use whatever you want. 2 teaspoons of that. Heaping teaspoons.
Hold it up
Then-
here.
It
There you
doesn't
go,
have
it's
to be
okay.
exact. Baking soda.
All right, good job.
So we have 2 heaping teaspoons of baking soda. And now, the piece de resistance. Okay? Most people cannot have a universal indicator in their homes to tell them whether something is acid or base. So you can make your own. This is a homemade universal indicator. It is a red cabbage that's chopped up, put with water, put in the blender, and strained.
Good job.
Cabbage juice is a universal indicator. It also stinks. What, can you smell it? Oh, is that nasty? No. So
You
what
will.
we do here is we pour in,
Can you smell it?
and what happened to that? What color is it turning?
Stir rod?
No, it's not here. It turns blue. So what that means, yes, it smells, doesn't it? Aren't you glad that you sat up front? What this means now is that we have something that is basic. So now you can go around and test anything you want in the house using a little red cabbage juice to make sure if it's acidic or basic. But one thing I'll warn you, because my nephews did this and they took my sister's extremely expensive perfume and tested it. It is acidic, but it's also very expensive. So don't go ahead and do that.
Stirring rod?
So
Right there?
we have a stir rod?
No, I guess that's no.
No? No, that's not it. Well, we don't need
Hold
it.
on just a second.
Now,
She's going to.
how do we make this work? We take a beaker. You can just use a measuring cup. And you put in about half a cup of
She's getting a stirring rod if you want to wait just. here you go.
vinegar, okay? And one thing
Thank
that you
you.
do want to do is stir this and make sure you have everything off the bottom there. Doesn't that look good? Yum. Okay. You ready?
You want to
Take
stand
this.
over here on this side?
And pour it in.
Fast.
All right, fast. Now, so this is something, if you want, you can do at home.
You have it on your
Notice
hands?
that it turned colors again. The reason it turned colors is because you added vinegar, which is acidic, to it, and it turned it so that it was less basic. So thank you very much for helping.
How about out
So
here in the
this
middle?
is the property of
Okay.
fluids that, as Brian said, as an aerospace engineer, he didn't really know this, but as a chemical engineer, these are the kinds of things that we know. There are certain fluids, certain elements,
Okay.
certain compounds that have what's called an unpaired electron. And because of it, they are paramagnetic. So what that means is they will stick to a magnet if they are paramagnetic. So we're going to test two fluids and see which one is paramagnetic. We have liquid oxygen and liquid nitrogen. So Brian, which is the one you're going to do first?
Let's do the nitrogen first.
We're going to do the liquid nitrogen first, okay? So we have a dewar. This is an enormous magnet. So if you have anything magnetic, don't get too close to it. And what we're going to do
Are we ready?
is pour this through.
Is anything happening?
Do you see anything happening? What? Right, it's getting all steamy. Do you see any of it sticking to the magnet? No. So it's not paramagnetic. So let's try oxygen. And this is liquid oxygen, which is actually not very easy
Got it?
to come by.
Okay.
And in fact, Elaine has been cooking it up all morning. So we'll take liquid oxygen and pour it through the magnet. Can you really see it?
Start to stick.
And what you'll see, even though it's, I don't know if you can see it with the
Do a little faster this time.
camera here. Can you focus right between the two? Yeah. Okay, we'll pour it through. You will actually
Underneath
getting throughout here liquid oxygen that actually sticks to the magnet. And liquid or oxygen is paramagnetic, and we use that property in a lot of research. For example, if you do something like electron spin resonance, you use the fact that there are certain compounds that are paramagnetic, and you can follow them using a magnet. An ethanol car is called that because it's a model of how a car runs. If you take two fluids, a gas and oxygen, and you ignite them, you get something called combustion. And that's how your car runs. So this is a model of how combustion works. Like that. Let's try another one. Oh. Oh. And now the best one, hopefully. Oh, you didn't do the last one.
Oh, the big
Yeah,
one.
one more.
All right, stand back.
Stand back. Oops, sorry. Sorry, maybe the people in the first row should have used safety glasses. Thank you very much.